All right, and so now we actually going to continue off where we left. So now remember what we have discussed. Just to remind you, we spoke about the quality of our vapor, right? And then we looked at the TV coordinates for saturation conditions and so forth. So now what we're going to do here, we're going to look at the PT diagram, right? So the PT diagram, it's a diagram that actually looks like this, which is called the phase diagram. Why am I saying it's a PT diagram? Because the variable that we are looking at over here, it's pressure and the temperature. Yeah? So here are the most important points that will actually help you to understand how does the PT diagram actually works, right? So remember here like I say, PT, we more of temperature and pressure. So these statements, they're based off the temperature and the pressure of our pure substance. So in this case, most of the time, like I said, we use water. So let's have a look at the first statement, what is basically happening, and then we'll analyze that afterwards. So now having a look at this first statement over here, we say let us now consider another experiment with piston or cylinder arrangement. Suppose that the cylinder contains 1 kilograms of ice at negative 20 degrees Celsius at 100 kilopascals. So if now we start from the solid because we are talking about ice, right? On the previous lessons, we were actually talking about the liquid water to water vapor. We never spoke about the solid state, right? But here, this is what I want you to understand, okay? If you have your ice, which is the solid water, right? And then the temperature of your solid water, initially it is negative 20 degrees Celsius at this constant pressure of 100 kilopascals. So now when you supply a heat into the system, once more again, into the piston or into the cylinder arrangement, remember we have the container and then we have the cylinder, which has this compressor over here, and then we have the ice, right? So if we supply heat into our system, what's going to happen? Remember, the system, it is closed. What is going to happen with the temperature? The temperature will most definitely increase, right? But remember, when the temperature increase, what's going to happen with the specific volume? The specific volume will most definitely increase. But you need to understand that for water, normally the specific volume, it is not greater than the specific volume of the solid. But for other substances, the specific volume, it is much more greater. Okay, that's another point that I want you to pay attention on to. But either way, when we supply heat onto our system, the temperature of the system will most definitely increase and the specific volume will increase slightly, okay, when we supply the heat. So remember, the initial temperature is 20 degrees Celsius and then we heat the system. When the temperature increases, it increases maybe to about 0 degrees Celsius. So when the temperature increases from negative 20 to 0 degrees Celsius, therefore our ice will start to melt to form what we call the liquid. But you have to understand that when the temperature reaches 0 degrees Celsius at a constant pressure of 100 kilopascals, we have saturated solid. So what do I mean when I say we have the saturated solid? We have solid with a bit of liquid. So meaning here our temperature is negative 20 degrees Celsius, right? And then there will be a phase change from negative 20 to 0 degrees Celsius. Say here on this side, we have the temperature. Okay, let me try to draw it like this so that it makes sense to you to see this is what we have already spoke about. It's just that we never spoke about it starting from the solid. So if I have my thing like this, my Cartesian plane just like this, and this side I have temperature. So let's assume here we have negative 20 degrees Celsius. So from negative 20 degrees Celsius to 0 degrees Celsius, what's going to happen is from here to here, we have ice here, and then here we have saturated solid. Saturated solid, it means it is composed of liquid and the solid, right? So When we further heat our system, what is going to happen? Remember, from here, we're going to have melting process. Remember, our graph starts from there to there, right? Our graph starts from there to there. What's happening with my pen? And then here we're going to have the melting process, right? And therefore, if we further heat our system into the cylinder, maybe the temperature from 0 degrees to 99.62 degrees Celsius, now what are we going to have? Remember, when it gets, I'll explain this, and then here our temperature will be 9.62 degrees. Then we're gonna have saturated liquid, and then from there we're gonna have the equilibrium. From there again, we know the drill, you know what's gonna happen. So remember, here we have ice, right? Here we have saturated solid, ne? We have saturated solid, and then here we have liquid, right? We have the liquid because this is the melting process. So ice from this point to that point will melt until it becomes a total liquid. And then when we boil this liquid further to above the temperatures, our water to above temperatures of 99.62 degrees, we're going to have saturated liquid. And therefore this saturated liquid will further be at equilibrium to transform the phase from liquid to complete vapor over here, right? And so forth. Here we're gonna have super. So this is what we have already started with. This is what we are familiar with, right? It's just that we never started from the solid. We took everything from there to there, up there, from positive 20 somewhere there, right? So this is what we have studied. But here it talks about all of the three phases: solid, liquid, and the gas. Now here, number two, let's see what's going to happen. What is the case over here? What's the thing? Now, if the initial pressure of the ice is negative 20 degrees Celsius, and then look at here, the pressure here, it is high, and then we decide to lower the pressure to 0.260 kilopascals, right? And then heat transfer to the ice results in an increase in temperature to negative 10 degrees Celsius. Now you see, this is what is happening. At this point in time, when the temperature it is negative 20 degrees, at this lower pressure, look at this pressure, it's very, very low compared to this pressure over here. This is 100, this is like 0.2. This is a very low pressure compared to this one. So at the lowest pressure, and then we transfer a heat into the system, what is going to happen? The temperature will increase slightly to negative 10 degrees Celsius, right? So when this happens, this is what I want you to know. The ice will directly move to gas, or you can say the ice will directly move to vapor. That's what it is actually going to take place. And this process of ice moving from ice to gas, meaning which step did we pass, or which stage did we pass? It is a stage of ice moving to liquid. So in this case, ice will straightly move to the gas or to the vapor. So this process of ice moving to gas, it is called the sublimation. Sublimation, right? Sublimation, it is called the sublimation. So now when you take this gas, right, at negative 10 degrees Celsius, and then you further heat the system by increasing the temperature. So now what we call that condition, we call it the superheating of the vapor, which is what we are quite familiar with. We know that when we have vapor and we further increase the temperature of the vapor, that's superheating conditions, right? We are superheating it, or superheated vapor. We're going to have what we call the superheated vapor. So sublimation, it happens at the very low pressures. And when we increase the temperature, then ice will, from solid to gas, and then ice will directly move to the vapor, right? So that is the case over here, which is called the sublimation, meaning sublimation occurs under very low pressures. Now, finally, let's consider this situation whereby an initial pressure of the ice is little bit higher than what we had here at sublimation. So it's 0.6113 kilopascals and the temperature of negative 20 degrees Celsius. So what is the case over here? So now here we're going to have what you call the triple point, right? When we have about this pressure of ice. Remember, the sublimation is under this pressure, meaning for each and every pure substance, it has its own temperature for sublimation. It has its own temperature for what? For triple point. So now what is this triple point? Triple point, it's simple. It is whereby our pure substance will be existing in all of three states, right? So meaning the triple point of a substance depends on the temperature and pressure at which three phases such as gas, liquid, and solid of the substance coexist in thermodynamic equilibrium. Also, it is the point at which three curves are met: sublimation, fusion, and vaporization. I'll discuss these curves on the upcoming slide. So basically, this is what is happening, okay? So what matters here is we look at the pressure, we look at the temperature. So the pressure and the temperature, they will give us what we call the PT diagram. Now, at higher pressures, it is what we are familiar with. If you want to take your ice and then heat the system, take your ice into the system, heat the system at higher pressures. It is what we are familiar with. Take your ice at the very same temperature, right? And then lower the pressure, you're going to get what you call the sublimation. Take your ice once more again, which is solid, at the very same temperature, which is negative 20 degrees Celsius, and then increase the pressure above the sublimation pressure, which is 0.613, and then you will get your triple point. So basically, in short summary for you to understand, at 100 Kelvin is what we are familiar with. For water, right? We are talking about water over here. You need to understand. At pressure of 0.260, which is lower pressures, we are talking about the sublimation. At the temperature that is above the sublimation pressure, at the pressure above sublimation pressure, which is this pressure over here, we have the triple point for water, by the way. Okay, meaning for each and every pure substance, it has its own sublimation temperature, it has its own, pressure, it has its own sublimation pressure, it has its own triple point pressure, okay, when it's solid. So now, having a look at this diagram over here, we have curves. Basically, we have three curves, just like how I explained here: sublimation, fusion, and vaporization. So now, here's the sublimation curve, right? And then here is the fusion curve, right? And then the remaining curve there over there, it will be our vaporization curve or vaporization line, right? So now let us dwell into this graph to understand what is actually taking place. Now let's start with the sublimation curve. I said to you sublimation, it happens at the lower pressures. So now on this side of the Cartesian plane, we have the pressure, and we can tell that the pressures over here are very low. So you can tell that when you have low temperatures, negative temperatures, remember, temperature increases as you move in this direction. Same applies to pressure increases as you move into this direction. But at this point over here, we can see that the pressure, it is very low. And then the temperature, it is very low. So when you want to increase the temperature, what is going to happen? The pressure will also increase slightly, but under the very low pressures, and therefore we're going to have the sublimation. So that means your substance from A to B will turn from where? From solid to gas or to vapor, right? So that means this line over here, which is line AB, it shows us that from A, we have a solid. From B, we have a vapor pressure because of sublimation. Why? Because we have low pressure, we have low temperatures of our solid. So obvious, if something, it is under low temperatures, so that means it could be solid most of the times. So this solid will turn into vapor, just like how we explained on the previous slide. Right? I hope that makes sense. And then now we have the triple point. Remember, I said to you, when you increase your pressure, let me do it like this so that you can even understand it much more, way better. So let me do this. Remember here, our temperature is going to be how much? Our pressure over here is going to be around 0.2, and then the pressure over here, when we go up, obviously the pressure increases. It's going to be around 0.6, for an example, right? So we can see that for water, because we are talking about water here, which is our pure substance, when the pressure is 0.6, we have a triple point. And at triple point, you see all of these curves together. Now it is explaining the statement over here that also it is a point at which three curves are met. Which curve? Sublimation curve, fusion curve, and vaporization curve. So meaning all of these curves, they meet here. Sublimation comes here, fusion comes here, and then the vaporization comes here. They meet here at triple point. So at this pressures over here, which is 0.6. So at this point, once more again, you have to know that our pure substance has all of the three phases, right, which is solid, liquid, and gas. This is all of those phases coexist at this point of time. And then we can see that from C to D, we can see that if this pressure, it is constant throughout, it starts from solid, we have this, then we have that, and so forth. So here is a transformation from solid to vapor again. And then now let's talk about the fusion. Fusion, basically, it's actually a line that separates the solid phase and the liquid phase. And these lines, by the way, they are equilibriums. So fusion line, it separates the solid phase and the liquid phase, right? So most of the times, if you want to jump from here to here to here, now we have what we are familiar with, which is about 100 kilopascal. When our pressure is all about 100 kilopascal, where your solid through this fusion line will turn into liquid, and then from liquid through this vaporization line will turn. And you can understand again by just looking at the temperature. Look at the temperature over here. It's a solid, right? And then we increase the temperature, we increase at this pressure, which is 100 kilopascal. We increase temperature, and therefore we have the liquid, which is what I have explained when I was talking about this graph over here, whereby the pressure, right, whereby the constant pressure was 100 kilopascal. So that means the pressure is 100 kilopascal, and therefore the temperature here, let's say it's negative 20 degrees, for an example, and therefore the temperature here is going to be 0 degrees, and the temperature over here is going to be 99.6 degrees Celsius. So that means from solid at high pressures, from solid through the fusion line, right? This is the equilibrium. This is whereby the composition for saturated solid and saturated liquid is equal. Hence why the fusion line, we call it the equilibrium line, meaning saturated solid and saturated liquid are equal at this point in time. And therefore, from this point to that point, and then here we have another equilibrium, which is F. Now we have the vapor. So this side, we're going to have saturated vapor, and in this side, we're going to have saturated liquid. So at this line, which is equilibrium, once more again, it's whereby saturated liquid composition is equals to saturated vapor composition. You understand what I'm saying? This is what we are quite familiar with, by the way. Okay. And then as we go up with very high pressures, remember 20 megapascals, or remember those pressures, not 40, it's supercritical, but 20 of water, 22, I think 22 comma something. Remember, we did that on the previous sessions. So 20 megapascal, 22, around there, we can have what you call the critical point. Remember, what did we say? What is the critical point? It's where we cannot distinguish the phases. We cannot distinguish the liquid and the vapor at this point in time, because we have a very high pressure and we also have very high temperature. We can see here, we also have a very high temperature on the side. Okay. And then this line over here, which is GH, it's all about superheated, right? It's all about superheated. This side over is going to be superheated, and therefore that's it about the phase diagram or the PT diagram. And then now having a look at this table, we have different substances, for example, normal hydrogen, for solid, liquid, vapor, triple point. Remember, for triple point, remember, we are talking about the temperature and pressure, right? We said that for water, we said that our pressure in degrees Celsius was negative 20 degrees Celsius, right? And then our pressure was, temperature. And then our pressure was how much? 0. I think it's 211. Okay, let me go back. The pressure was for triple point, 0.611. Made a mistake, 0.6113 kilopascal. So this, it is the temperature and pressure for triple point for water, meaning solid, liquid, vapor. Triple point data for water, it's going to be this one. But for other substances, for an example, for a normal hydrogen, we have this temperature and that pressure. For oxygen, we have this temperature and that pressure. Remember, we have different substances, we have different pure substances. We cannot only talk about water, we need to account for other substances as well based off their pressure and their temperatures under these conditions, okay? So then on the next video, we'll look at the examples. Then thank you.